right. So let's go. Let's let's check this problem here. This problem is a classic one about conservation of energy when involves a thermal energy as well. Um, so what we can do in this problem? Let's read it first. So a 900 crate, Newton's crate. So this is going to be the weight, right? Slides 12 meters down a ramp that makes an angle of 35 degrees with the horizontal. If the crate slides this is really important, guys, at a constant speed, so this is important, constant speed, constant speed, how much thermal energy is created? Well, this problem here states a lot of important things. First of all, he he wants us to calculate what is the thermal energy, right? The thermal energy here. So the thermal energy is, when we talk about this kind of problem, you need to remember that the thermal energy is always related with friction, okay? Always related with friction. In which way? When we have the thermal energy, it will be equals to the work due by the friction force. So it's going to be the work of the friction force, friction, okay? And that means it will be the friction times the distance when about, I mean, that this friction is applied to, okay? So this is our equation that we need to remember, okay? So I will highlight here just for you guys to remember, okay? Just for you guys to remember. So this is important. Now, okay, but I mean, how how we will figure out who is the friction force? Well, this problem gave us some hint. For example, the hint here that I'm talking about, it is the constant speed. If you remember, guys, the first law, Newton's first law, is when all the sum of all force, if we have the sum of all force when they are equals to zero, that means we don't have acceleration, and that means constant speed. So if we have a constant speed, that means the sum of all forces in our system here, it will be equals to zero. Okay, but I still don't get it. How we can correlate, I mean, the friction force, it's not, because how we know friction force, if you remember, if you start to attack using, oh, I remember the friction formula, it's going to be some kind of coefficient times the normal force, right? This is the force, I mean, this is the friction force that you remember, the formula. But it's not this formula that we're going to use. We have this one here. I know, but how can we correlate it? Let me show you. If you, I drew here about, make a drawing here with our normal force and our weight. Normal force always perpendicular with the surface. The weight always going directly into the center of Earth. But if you remember, guys, every time when we have a vector, we have components. So that means we have a component here and a component here. That means we have a component here and we have a component here. Okay, but I mean, what that means, if we have components, we have our reference axis here. So this guy here will be our y, right? And this guy here will be our x. Agreed? From the weight. Well, the only one that will do some work here is going to be, I mean, the weight in x, because this guy will have cosine of 0. Cosine of 0 is equals to 1 here with the distance. But this guy brings more information than it looks like. If you remember, every time when we have a friction, it's because it's opposing a movement. So if this guy is going down like this, if my velocity is going this direction here, that means my friction force is going directly positive, right? So I have a friction force, let me put as a red here. I have a friction force like this, agreed? This direction. Whoa, so we can see I can see a correlation now because take a look. If I use if I use this friction force and this weight in x, because the weight in x is pointing to this direction. To be honest, guys, this is why every time when we put something on a ramp, every time when you put something on a ramp like this, what makes it um, goes in a certain direction. For example, this one here, it's gonna be the weight, the component. I mean, the x component of the weight that will be fighting against the friction here. So this is the why this stuff here, the crates goes down, right? So what that means? That means my friction force must be equals to my weight in x. And the reason it's because I have constant speed. Okay? This is the why. I have constant speed. So let me clarify something here. Now that I have this guy, how can I calculate my weight in x? Well, my weight in x, this theta, it's the same of 35. Okay, so that means my weight in x will be equals, if you remember, this cat here, this line here will be opposite to the theta. So it's going to be the weight times the sine of 35 degrees. Okay? So my weight x will be, what is the weight? 900. Okay, 900 newtons times the sine of 35 degrees. So my weight in x is equal to what? Let me calculate here using my super hyper calculator. So it's going to be 900 times sine of 35 degrees. So it's going to be 516 newtons. So, okay, I got my weight in x here. So my component of the weight in x. So this will be the same thing that I have for friction. Well, if I have the friction, I just need now to plug it in this friction force here on this formula for the thermal energy and multiply by the distance. What's going to be the distance? The distance that this force will be applied. That's going to be the whole hypotenuse of this guy, and I have it like 12 meters. So that means uh, my thermal energy will be 500, agreed, 516 newtons times what? 12 meters. So my answer will be, okay, times 12. This will be 6,194 joules, right? That I can approximate to 6,200 joules. So this is how I calculate my thermal energy based on the friction force. Okay, so what I did, I remember that there is a correlation between friction force with thermal energy that is based on work, right? So I just had to calculate who is this guy. So I remember that every single vector has components. So my weight here has a component in x, that will be opposing the direction of the friction here. Okay, so I just calculate this weight in x, and I remember that the problem mentioned that they are in constant speed, and then I apply everything, all the numbers here, boom, I got the thermal energy. Okay, I hope you have enjoyed it, and guys, let's do some physics.